Hey there, Deep Diver. Ready to really push the boundaries of what's possible. Today, we're diving into optical black holes.
Optical black holes.
Yeah, you heard me right. We're talking about recreating black holes.
Wow.
Right here on Earth, using light.
With light.
You with me on this one?
Absolutely. It is a fascinating area of research for sure.
Okay, so before we get into I could ask why. Why are scientists trying to build black holes in a lab? Isn't space weird enough already?
You would think so. Right. But that's the thing about science, isn't it? It's always pushing those boundaries. And this isn't just about recreating something cool, although it is undeniably cool. This is about testing our understanding of one of the most just mind-bending theories out there, general relativity. Imagine having a mini black hole sitting right there on the table.
Yeah.
And we could just study it up close.
Oh, the things we could learn.
What we could learn.
Okay, so you sent over some research. The title of it is a little complicated. Optical analogues to the equatorial Kerr-Newman black hole.
Right.
What's the gist?
So essentially, it describes how to create materials that can bend light in the same way that a real black hole bends space-time.
So bending light, how do they do that?
Well, that's where this thing called the scalar refractive index comes in.
Okay.
You can think of it like a recipe for how much a material will bend light.
Okay.
And it turns out that for certain black holes, we can actually calculate this index, which gives us a blueprint for building an optical black hole.
So what's wild to me is they're using materials you can find at Home Depot. We're talking water, glass, plastic.
That's true.
Who knew?
It's true. Although it's a little more complicated than just, arranging some glass and water in a particular way.
Right.
Imagine having to create these intricate structures that manipulate light.
Yeah.
In very specific ways. And of course, there are limitations.
So not a weekend DIY project.
Not quite.
Yeah.
The research emphasizes that these simulations are most accurate at a really, really tiny scale.
Yeah.
We're talking like micrometers.
Microscopic.
But even then, just seeing light behave around these simulated event horizons in the way that was predicted,
Yeah.
huge.
Okay, so microscopic recreations, but the science still holds up.
Absolutely. And to simulate how light waves would actually move through these really tiny structures, they use what's called a finite difference frequency domain solver. Essentially, it's a very sophisticated computer model, like a virtual laboratory for light. And using this, they modeled a bunch of different optical black holes, including a Schwarzschild black hole, your classic no-spin black hole.
Right.
And tested them with various impact parameters.
Okay, now hold on. Impact parameters, what do those have to do with black holes?
Good question. In this case, the impact parameter is essentially a measure of how close a beam of light gets to the black hole before it's affected by its gravity. They tested a range of these.
Sure.
And for the most part, the simulated light followed the predicted path really remarkably well.
Wow.
Imagine seeing the bending of space-time right there on your computer screen.
Way smaller than a computer screen, though, right?
Exactly. And they also looked at more complex types of black holes, like the Kerr-Newman black hole, which is both spinning and charged.
Okay, so did the simulations work for those as well?
They did for the most part, yes. Especially for co-rotating black holes, where the black holes spin and the light's path are going in the same direction. The simulations showed the light being dragged along with the spin, just as general relativity predicts.
Wow.
Yeah.
So we're talking pretty convincing evidence that we can create these mini black hole environments in the lab.
It's looking very promising, although like any experiment, there's always room for improvement.
Oh, of course.
One challenge is actually creating that ideal gradient in the refractive index.
Okay.
So in these simulations, they had to simplify things a bit by using concentric rings of material, each with a constant refractive index.
So instead of like a smooth, gradual change, it's more like a staircase.
Exactly, like a staircase. And that can lead to some differences between the simulation and what we would theoretically expect.
But, in a way, aren't those differences interesting? They highlight the limits of our models and what we can achieve in the real world.
Absolutely. And in fact, they actually did some calculations to see how much these imperfections might affect the light's path.
Okay.
And it turns out that with enough rings and very precise manufacturing, you can actually get incredibly close to the actual path that light would take near a black hole. We call that path the geodesic.
Geodesic, the path light takes when it's bent by a black hole's gravity.
Precisely. Yeah. And the really exciting part is that these simulations allow us to explore scenarios that we could never directly observe.
Like what?
Like, what happens when light gets really, really close to a black hole? Does it just completely vanish? Does it get trapped in orbit? These are the questions.
Those are big questions.
They're big questions. And that's the thing about science, right? It's not always about having all the answers, but rather about asking the right questions.
Love that.
And these simulations, as intricate as they are, highlight that there are still so many mysteries left to unravel.
Okay, so you've definitely piqued my curiosity. Speaking of curiosity, the research mentioned that these optical black holes aren't just good for studying light. Apparently, they could also teach us something about sound. Now, how is that possible?
That's where it gets even more interesting.
Okay.
There are these fascinating parallels between how light acts around a black hole and how sound waves behave in certain materials.
Okay, now you're blowing my mind. How can sound even be similar to light? I mean, they're totally different things.
Yeah, so it all comes down to something called the acoustic metric, just like gravity warps space-time.
Right.
The way that sound waves travel can actually be warped by the properties of the material that they're moving through.
So are you saying we could create like an acoustic black hole? One that traps sound instead of light?
Precisely.
Wow.
And researchers have actually built these acoustic analogues in the lab using special materials called phononic crystals
Okay.
that can manipulate sound waves in very specific ways.
Phononic crystals. It sounds like something straight out of Star Trek.
Right.
But what's the real world use here? Why build a black hole for sound?
Well, the applications are actually surprisingly practical.
Okay.
Acoustic black holes could lead to breakthroughs in things like soundproofing.
Really?
And even energy harvesting. Imagine capturing sound energy that would otherwise just be lost.
Now that's what I call a tangible benefit. Okay, so we've got these mini black holes for light, black holes for sound.
Yeah.
Anything else these simulations can help us understand?
Well, the researchers are especially interested in testing out something called Hawking radiation.
Hawking radiation. Okay, now that rings a bell. Wasn't that one of Stephen Hawking's big ideas?
The one and only.
Okay.
It's this mind-blowing concept that suggests that black holes aren't completely black after all.
Okay.
According to Hawking's theory, black holes should actually emit a faint glow of radiation because of quantum effects happening right there at the event horizon, you know, that boundary beyond which nothing, not even light, can escape.
Right, quantum effects. So we're really going down the physics rabbit hole now. So how do these optical black holes tie into that?
Well, they give us a way to potentially observe something similar to Hawking radiation, but here on Earth.
Okay.
Remember those similarities between light and sound waves we talked about?
Yeah.
Well, it turns out that Hawking radiation should have an acoustic counterpart as well, meaning we could potentially create sound from an acoustic black hole.
Wow.
Yeah, in theory, yes. I do have to emphasize that actually detecting this acoustic Hawking radiation is incredibly difficult.
Okay.
We're talking about extremely faint signals that are really easily drowned out by background noise.
So that's why they call it a faint glow.
Yeah.
It's like trying to hear a whisper in a hurricane.
Exactly. But if researchers can figure out how to overcome those challenges,
Right.
it would be a massive discovery. It would further support Hawking's theory and potentially even give us new insight into the nature of quantum gravity itself, that holy grail of physics that seeks to unify general relativity and quantum mechanics.
Quantum gravity. Now that's a topic for a whole other deep dive.
Yeah.
But for today, what's the key takeaway you want our listener to walk away with?
I think the main takeaway here is that these optical black holes are so much more than just fascinating curiosities.
Right.
They're really powerful tools that are pushing the boundaries of our understanding in fields ranging from general relativity to quantum mechanics.
Mm-hmm.
And who knows, maybe someday even our understanding of the very fabric of reality itself.
I don't know about you, but I'm feeling a little smarter after that conversation.
Good.
But before we get completely lost in the vastness of the cosmos, there's one more thing I wanted to ask you about.
Yeah.
So we've been talking about creating these artificial event horizons using light and sound, but the research mentioned something about counter-rotating black holes causing some issues for these simulations. What's going on there?
Yeah, that's a really interesting aspect of this research. When they tried to simulate black holes where the spin was the opposite of the light's path, we call that counter-rotating.
Right.
Things got a little weird.
Weird how, what happened? Did the simulation just crash?
Not quite. It's more like the math behind it just kind of broke down. To create these counter-rotating scenarios, the refractive index would theoretically have to become infinite,
Okay.
which just isn't possible in the real world.
Right. Okay, so the simulation hit a cosmic speed bump. But what does that tell us about real black holes?
That's the million-dollar question, isn't it? It really highlights how much we still don't know.
Right.
Even with these incredibly advanced simulations, we're still just scratching the surface of understanding how light behaves in these incredibly strong gravitational fields.
So it's like we're trying to create a perfect replica of the universe in miniature,
Yeah,
but we keep bumping up against the limits of what's actually possible.
exactly. And that's okay. Those limitations, they actually help us ask better questions and
Right.
refine our understanding. It's all part of the process.
I love that perspective, embracing the unknown and using it as fuel to learn more. So for our listeners out there who are like me, completely captivated by these optical black holes, what's one thing you'd recommend they ponder? What's got you curious about the future of this research?
Well, we've talked a lot about recreating event horizons using light and sound.
Right. But what about other kinds of waves?
Like what?
Could we, for example, create an event horizon for water waves?
Now that's an interesting thought. Like a black hole in a bathtub.
It might sound strange, but the fundamental principles are surprisingly similar. And who knows what we might discover by exploring these possibilities. It's a reminder that even in the most unexpected places, we can find connections to the most mind-boggling phenomena in the universe.
I love that. Well, expert speaker, you've given us a lot to think about today. A huge thanks to you for taking us on this deep dive into the world of optical black holes, Hawking radiation, and the future of physics.
My pleasure.
And to our deep divers tuning in, thank you for joining us on this journey to the edges of knowledge. We'll catch you next time for another deep dive into the most fascinating corners of our universe.